Hi, now we are going to talk about hyperparameter optimizations and what are the optimization bias. But before we start anything, here we'll import all the stuff that is needed for this class. Right, so all the model we have already imported. Now, what we'll see in this lectures. So basically, we'll see like the need of hyperparameter optimizations. We'll see about the grid search CV and the randomized search CV algorithms. We'll see the different hyperparameters uh, that we use with the grid search CV. We'll explain the importance of selecting the good range of value. So if we have any hyperparameter, we need to give a specific set of value for that parameter. Right? We'll talk about that. We'll talk about the optimization bias. Right? And we'll also identify and the reason when to trust and not trust the reported accuracy. Right? So let's see. So as a motivation, so this hyperparameter optimizations uh, generally we need because we need to have the good models, right? That works on the cross-validation data or the test data, right? And for that, a good hyperparameter gives you the good model, right? So we want to find a model which gives you the highest accuracy on the cross-validation data, right? And then so that now we can use that model to test our so that we can use that optimized model, right, to test on the real world data set, right? And again, the good model having the best hyperparameter, right? So good model is like any model is related to any data has a specific set of parameter. If you found that optimized parameter, that means you have found the good model, right? So in order to improve the generalization performance and finding the best value of the important hyperparameter of the model is necessary for almost all the model in the data set, right? So picking good hyperparameter is important because if we do not, we might end up either overfitting or the underfitted model, right? Now, now the some way to pick hyperparameter is we can do the manual approach, right? Or the or like expect or like ex, expert can suggest you, right? And then the second approach is the data driven or the automated optimization technique, right? So manual approach we have already discussed, right? Like so basically we'll talk about how to kind of do this data driven or automated optimization approach, right? So the manual approach, as we have seen, it's like we can we can find the best hyperparameter like the max depth or the C, but the disadvantages for the manual approach is it takes a lot of time, right? It is not reproducible approach, right? And in complicated cases, right, it might be the worst scenario, right? So data-driven approach is the much more kind of optimization way to choose the hyperparameter, right? So basically, right? So we have the many hyperparameter of the different type. Like we have the continuous value, we have the categoricals, we have the integers, so all the different type of the hyperparameter we have, right? And then we consider that our search space is a big like basically we try to find a multiple hyperparameter. We try to check with the multiple hyperparameter, and based on that, we try to find the best hyperparameter, right? Now, now our hyperparameter, our automated hyperparameter looks in this format, right? So here, first we have the parameter grid. Now, this parameter grid is what? Basically, it's a set of all the parameters and their value with the specific range we can define, right? Let's say that if you are using a decision tree algorithm, there you can define the max depth. You can decide that like you can take a value from 1 to 10 or 1 to 20 or 1 to 50 as a max depth parameter, right? A model will automatically kind of choose one value at a time. Now we'll pass this parameter grid to the cross validations, right? But This cross validation have the training data from the data set. Now when you apply the cross validation with the training data and when you pass this all set of parameter, it will give you the best parameter. Now what we do is basically we retrain the model by taking all the training data and the best parameter, and then we find the final model. So basically we evaluate the final model using test data. That is how the parameter this automated parameter approach looks like, right? Here we have loaded our Spotify dataset, right? Here we have splitted our dataset into training and testing. Uh, we have separated all the type of category we have. We have made a column transformer. So this is our preprocessor now, and now we are making a pipeline by taking preprocessor and SVC. This is our pipeline now. Now here we are using the SVC model, right? Now the SVC can have the multiple value, right? And so this is the model that we are trying, right? So we can try the max depth value. So here we can use this pipeline, right? So we can even try, like here we are using this decision tree classifier over here, right? And for that, in the parameter grid we are passing the max depth parameter. We are taking the value between 1 to 20, right, which is our max depth parameter, right? And then this pipeline we are passing to the cross validation score, right, which will give you the score on the validation data. And here we're checking that if the value is greater than the best score. So currently our best score is 0. So we'll change our best score, and basically we'll keep updating our best score. And here if we found the new best score, we'll kind of set that parameter. And now we are storing all the value like the depth and the mean scores, all the value we are storing in this result, right? So here we can check. Now once we do this, we can check the best parameter. Here we can see that the best max depth parameter, best parameter is 5, and the best score is 73% that we are getting. We can also try the SVC, right? So here we have made the pipeline. This is our fit method. After that, here we are passing our pipeline, this SVM pipeline, to the cross-validate function. This is the value we are getting with the default parameter, right? And again, here we have got this output at the default parameter. But consider that in SVM we have a lots of hyperparameter. We have two hyperparameter made. One is gamma, the other one is C. So first it will choose all the value of the gamma, and then it will choose all the value of C. And because we are using the cross validation, so it will kind of take a loop, or it will apply all the model during the cross validation as well, right? So basically it will become much more exhaustive, right? It will become much more exhaustive to try every combination with each fault, right? Here we are trying to do so. So this is the first we have taken the different value of C, then the different value of gamma. How many value we have? We have total 6 value of C and the 6 value of gamma, right? And then we are using the every value of C, then the like every value of gamma and the C. So again, if you choose the every value of gamma and C, it will be 6 into 6, so that is 36, right? So it will be 36 combinations. So here in this pipeline, we are trying a 36 combinations, right? And then we are also using cross validation. So cross validation, now we have the 5 more. So for every combination, we are applying the 5 different kind of model. Here we are trying 5 different model because of the cross validation, right? By default, this cross validation value is 5, right? So the total model will be 36 into 5, right? So I think it will be 180, right? So here with this parameter, with this 5-fold cross validation, we are trying 180 time of our models, right? So we are testing 180 model, right? And then again, the score is same. So here we are checking the best score and the best value and the best hyperparameter, right? So here we are checking what is the best parameter. For the gamma is C is this gamma value, we have found this, right? So the best score we are getting as 0.73 as a best score we have. Here we have converted all the value to the data frame. Now we are sorting the value by mean CV scores, right? So here we can see that. So our best C and the gamma value is this, where our mean CV score is this value, right? So in this way, here Now we can try here. What we're trying is we have created so this is our main CV score, right? So here what we have done is we have created a heat map, right, using this score. So we have taken this mean CV score and then we have converted it into a heat map with a different value of gamma and the C. So here we have all the value of gamma, we have all the value of C, and then the total value we have. And we can check that here our approximate score is 74% with the gamma value of 0.1 and the C value of 1, which is true, right? Which is true, right? So the total parameter grid value we have is a 36, and again the like 36 into 5 is 180 model, right? I've already told you. So we are training a 180 model in this. Now, after we found the best parameter, let's say that here we have found our best parameter is C and the gamma value, right? We can use that best parameter over here. So in the SVC, we are passing the best parameter value, and then again we are applying the fit method on the entire training data, right? And this is our pipeline looks like, right? And then after that, we can check the score. So our score is 75%, right? So our score on the test data is the 75%, right? So like what we have done, so basically we have done is we chose the parameter grid. We had a data set, we split it into two part, training and testing. Now in the training part we are passing our cross validation, right? Here we have to choose the model. In the cross validate function we have to choose the model. Then for that model we have to pass the different set of parameter in the using a parameter grid, that was using a dictionary. Then when we train our model, right, that basically, so our goal is to find the best parameter. So by doing so we found the best parameter. Now once we found the best parameter, now we want to retrain the entire model using the entire training data. This time we will not do the cross validations, so we'll directly train the model using the best parameter which was found with the cross validation score, right? And then the entire training data will retrain the model. Once we found the exact retrained model, right, now we want to test that model on a test data. So here we'll take our test data, right, and like we'll test our test data using the final model. That will be our final evaluation, right? Now this process is very much common, right, in the machine learning domain, right? So that scikit-learn has created a standard method for that, right? So those method is grid search CV and the randomized search CV. Now here the CV stand for the cross validation. That means if you use grid search CV method or randomized search CV, so it will automatically do the cross validation, right? You do not have to apply the cross validation over here, right? That will automatically do the cross validations with it. Now let's talk about the grid search CV, right? So to import it, we'll simply do sklearn.model selection, import grid search CV, right? Now here we are getting a pipeline from the using preprocessor and SVC, right? Now this is a pipeline we have created. Now this is how we have to specify the parameter grid, right? So let's say that if you want to use the, the count vectorizer, right? So here we are setting that column transformer. So because it is a type of, because it will be in the column transformer process. So first we'll name as a column transformer, double underscore count vectorizer, double underscore max feature. So here we are trying a different max features, right? Then because this gamma value related to C, so we'll see SVC double underscore gamma, the different set of the gamma value, same as the different set of the C value, right? So we have to specify in this format. Here we have the three set of parameter grid, right? After that, here we are now creating the object of grid search CV, right? So we have this SVM pipeline. We are specifying the parameter grid. Here we are setting the n job as a -1, right? We are setting the stray return train trace score is true, right? And this is our object of the parameter grid that we have got. Now we can use this object. We can directly apply the fit method. Now when we apply the fit method on the grid cell CV, it will use this pipeline. It will use this particular parameter grid. It will use kind of cross validations, right? And fit the method, right? Fit the model, right? After that, we can check the best score directly, right? So it can give you the total best score. So we are getting the best score. We can also get the best parameters, right? So we have this built-in value. So this best score and the best parameter we have got, right? Now we can also visualize our result. We can get the result with the dot CV underscore result underscore, right? We can get the all the result in this attribute. Here we can see the all the results, right? So how many model we have trained? Here we have trained 215. Basically, it's I think it's 216 model starting from zero, right? We have this 216 model, right? And yeah, and again, what value we are getting? We are getting this all the different parameter. How much time does it take? What are the parameter distribution? So this is the entire parameter value we have. This is our score on the split. So first zeroth split had this score, first split had this score, and so on. Then also we have this mean test score, right? We have the ranking of the model, right? The rank test score we have. Again, we have the mean train score, right? So we have got lot of value, lot of information here we have got, right? Now, what we're doing is here again the same result we are seeing, but now we are setting this rank test score as an index, right? So we are setting this rank test score where it is this score as an index we are setting, and then we are sorting that index. So it will be in the ascending order, right? Now when we check this, here we can see that. So the rank 1 model, again the rank 2 model, rank 3 model, rank 4 model, right? We can see that. Again, we will see the repeated value, but we are interested in the rank 1 model because rank 1 model means best model. This is, and this is all the parameter we have, right? And the total score we have got as an for the train score, we have got 88%, and for the where it is, this mean score type, no, not this one. So mean test score is 74%, right? So our test score is 74% and our train score is 88%, right? We can also specify the few parameters. So here we have specified the only few value, right? And then we are applying the same approach, right? So now it is much better, right? So now we are only selecting the few features to look on, right? We are not looking at all the value, right? And we can also do the score. So how we can do the score? So basically grid search CV, right? Like basically instead of like other than searching for the best hyperparameter value, this also fit the new model on the whole training set with the parameter with the best result. So we can call the score method on the test score, right? So you do not need to find the best parameter. Then based on that best parameter, we need to find the best model. And then after that, we can test it on the test score. We do not need to do that. We do not need to recreate the new model. The grid search series can do that for you, right? Means you can directly call the score method. Here we have got the score result as in 75%, right? Again, we have used the end job as a -1. This means that here, when we set end job as a -1, this means that we want to use all our compute power, right? And we want to run all the compute power in parallel, right? So we want to run all the compute power. That's the reason we have set n jobs equal to -1, right? So that means your task can become much more quicker, right? And this syntax is for the nesting of the transformers, right? We can use double underscore to go more deeper into the like more deeper into the object, right? And this is the pipeline of the SVM looks like, right? Now we can choose, here we can choose the different range of the C value, right? So yeah, so we can also like, so consider that here we have this, like when we choose CSN 1 2 3 till 100, right? So 1 2 3 is very small, so basically we choose in this format, right? 0 0.01 0 0.1 1 10. So basically we multiply each element by 10, right? Or you can also choose in this format, right? Both are same thing, right? Or in other, or we can also say that 10 raised to minus n, and n could be the any value, like n could be the value between -2 to or -10 to 10, something like that, right? Here we can visualize the parameter grid as a heat map. So for that we have created a function called display heat map, which takes the parameter, which takes the pipeline, which takes the training data. It applies the grid search CV, it applies the fit method on the training data. It gets the result, it checks the best scores, like here. After that, we check the main test scores, and then we are like here we are plotting our heat map of this scores, right? So this function basically it will take all the parameter and gives you the heat map directly, right? And here we can see that. So this is the first parameter value that we are trying, and this is the heat map we have got, right? So here we can see that our the score is 74% with the C value of 1 and with the gamma value of 0.1, right? So here what we can do is we can try a different range, right? Or like we have to be very much sure that that which range we are trying, right? So let's say that if you try this range, which is this log space value, this could be the bad range. If you try this lin space, this could also be the bad range. So basically we have to be very much sure that we choose the best range value as an hyperparameter, right? So here we can see that if we choose the bad range value, we can see that we do not get the further improvement, right? Right? And here what we know, so here we knew that our C value with the 1 was giving the 74%. So basically we have chose the, like here we have choose the all the value which is near to 1 and between 0.1 and 10, right? So that we can see that can we improve our model or not, right? So here we are doing the same thing, right? Here we are specifying the value of gamma and this, right? And again we do not see any improvement over here, right? Here we are again trying a different value which is closer to 2. So we are trying a C value which is closer to 2. So when we see the closer to 2, right? Now we can see that we have got the value as in 75%. So now there is a 1% improvement in our model, right? So now we know how to choose how to pass a different parameter in the grid system. Now we have a problem with this approach. Why? Because it tests a lot of parameter in our model, right? Suppose we have the five hyperparameter, and for every hyperparameter we are trying a 10 different value, right? So how many model you will be trying? Basically you will be evaluating 10 raised to 5 model, right? So you will basically you will see that the number of model that you will try is in 100,000 model just for the parameter, but the cross validation is still there. If you call the cross validations, right, it will be a lot more times, right? So now trying these many models just to choose the hyperparameter is not the good options, right? So this is a problem we have with the creature CV, where we try a different combination of the, or like where we try all the combination of the hyperparameter, right? So now we'll talk about the randomized search CV. Now in randomized hyperparameter, basically it's a more approach, more advanced towards the grid search CV. Basically in grid search CV, our algorithm try every combination, but in randomizer CV, our algorithm try only a subset of the parameter that you have passed, right? That means it is not going to try each and every parameter, each and every combinations, right? So here, first we have imported the randomized CV, again the same parameter grid that we'll use. And then the number of parameters that we'll try over here is like 216. So we have this 216 parameters, a total parameter in this we have, right? And this is the parameter grid that we have. Now we are passing this parameter. So the total parameter combination is 216. Now we are parting. Now we are using our SVM models, our pipeline models, passing the parameter grid. Now here we are setting the n iter as 100. That means we are saying that out of 216 combination, we want to try the 100 combination only, right? So here we are controlling, right, how much parameter that we want to do. Now which parameter it will choose? It will choose the random parameter, right? We do not have the control over which parameter that we want to choose again. So it will randomly select the parameter combination and try a different model on that, right? Here we can, after that, first, like after we get the object of that, now we are applying the fit method over here. After the fit method, now we are trying to check the scores. So here again we have tested based on the rank test score. So we have got the mean test score as a 74%, right? And which is a good, right? So our C value is 3, our gamma value is 0.1, and the score value we have got as in 74%, which is good, right? So our earlier model had tried a different combination and it has chose a 75%, but again, it's okay, right? And here again, still we have set the n iter, right? We have already discussed about how n iter work. Now we know how to control the number of iterations, the number of model trying. Now let's talk about passing. We can also pass the probability distributions, right, to a random search. Like over here, instead of defining our parameter over here, like here we have choose the different value of gamma, different value of C, the different value of this max features, right? Instead of that, we can pass the different numbers from the different distribution value, right? Here, so first we are importing this exponential log normalization, like log num, log uniform, rand in, which is the random integer uniform distribution, normal distribution, random this again, this is the random integer value. So we have imported all the distributions, right? Here we are just trying to check how the distribution looks like. So this is the distribution, like this is the value taken from the uniform distributions, this is the value taken from the uh, like from the normal distributions, this is the value taken from the exponential distributions, right? We can see that. And now, so our pipeline is this, right? So what we can do is here we can try the different value from the different distributions, right? So here we have choose that the random integer between 100 and 2000. So it will choose any of the random number between 100 and 2000 as a max feature. Same as we'll choose the random normal from the uniform distribution. Again, here we are choosing the log uniform distribution value, right? So again, here we have just given the range. Now, every time when the number of iteration happen, it will choose a value from this distribution, all three distributions, right? So we can also pass these value, and here we have passes this parameter distribution value, right? In the editor we have set 100. That means we want to try our model for 100 time, right? And then we have applied the fit method, right? After that, we can check our best score as in 72%, which is good, right? Now we can increase the number of iterations, right? And again, the C value is this and the gamma value is this we have got, right? We can also choose the C value is this and the gamma value is this. So sometimes people also try this method to choose the best hyperparameter, right? Now the advantages of randomizer CV, as we have already discussed in the grid search CV, right? We have tried basically in grid search CV we try every combination, but in randomizer CV we try only the, like we train the model only the number of times that we want to train, right? By choosing the random number from the different combinations, right? And it is way faster than the grid search CV, right? Now we can also search for optimal parameter with the successive halving method. Now what is this? So this successive halving method is an iterative selection process, right? Where we evaluate all the candidates, that means here all the parameters, right, with a small number of the resources, like the small number of the training data at first iteration, right? So here we can also check this documentation of this, right? But here to use this, first we need to import this halving random search CV, right? In this we are passing the estimator, we are passing the distribution, we are passing factor 2. So it will kind of divide all the value with the factor 2. Again, you can learn about this from this documentation, right? And then here we are applying the fit method, right? After that we can check the results, right? So here we can check the results. So here we have converted our parameter to the parameter string, right? So here we can check our parameter string. So this is the parameter string value we have for the different parameter, right? And here we can see how many number of resources we have used, right? Now there are a lot more fancier method we have, right? So we can also use a scikit optimize function, which is a different package than the scikit learn, right? Which was originally designed to get the optimized model, right? Basically, this scikit optimize uses a model-based optimization. Basically, it uses the Bayesian optimization algorithm. So here, in short, to find the best hyperparameter, best model, we use, or to find the best scikit-learn model, not scikit-learn, but to find the best machine learning model, we use a different machine learning model, right? So this is, and then again, there are a lot more fancier method out there, right? Like we have this hyper opt, we have this auto learn, we have the t-port, like these, like lots of model we have. Now let's talk about overfitting of the validation error. So what is that? So the question is, when we create a model on the validation using a training set, when we do the cross validation, we choose a different cross validation, different validation value, and then the different training data. Then why do we need to test our model in the end using the test data? Why not just use the cross validation on the whole data set? Why do we always need to keep aside our test data, right? So while while we do the hyperparameter search, right, we try a different combinations, right, and consider if our data set is very small, right? So and our validation data, that means if we'll try our model on the validation data, if that hit a lot of time, that means we are trying a model for a lot many times for a small data set, right? We suffer from the optimization bias. That means we have optimized our model by looking at all the example. This is what we can say, right? And that will be overfitted on the validation set. So when we test on our test data, that model will not be good on the test data. That then that is a signal that we have got the optimization biased model, right? So if your data set is not very big, right? If your data set is small, so do not try a lot more combination of that parameter, right? Now the optimization bias of the parameter learning. So again, so overfitting of the training data happens, right? So consider that we have this lots of parameter we have, right? So again, but sometimes we also get the, so if our parameter learns hard the training data, that time we get the overfitted situations. As an examples, during training data, we can search over a different decision tree, right? Sometimes we might get lucky and find a tree with the lowest training error by a chance, right? That time we can say that we have got the like like we have tortured our model a lot of time, a lot more time that it has given you the best model. That is not the how a machine learning works, right? Now this optimization bias of hyperparameter learning. So again, this was for the parameter learning. This is for the hyperparameter as well. That means we can try a different max depth value, right? And then let's say that on our like one of the many tree might have low validation error by a chance, right? So here, when we get the overfitting on the validation error, so when we try a different hyperparameter, right, to kind of best the best to find the best hyperparameter, that means we want to find the model with the good validation or like low validation error, right? So if we try a very different model or a very different hyperparameter, we might get lucky, right? And that time we might get a model with the lowest validation error, but that might not be the same scenario with the test data, right? Again, optimization bias. For optimization bias, consider this example. Suppose we have like again, like consider that multiple choice questions we have, like we have to choose between A, B, C, D with the 10 questions, right? So even though if you choose randomly, like we can expect of it 25% of the accuracy, right? But if we try hitting hard and hard, that means if we try uh, training our model for, let's say that if you try like if you train our model for 10,000 times, which is not a good scenario, right? You might end up getting the 82% accurate model, right? This is just a maths that we can calculate. So we have to be very much sure how much time, if we have the very low data, right? We have to be sure that which hyperparameter that we are trying, right? And here is an example for that, right? Again, I'm not going to kind of go through all the example, but you can read it out later on, right? And here is the second examples we have, right? Here what we're trying is, if we are checking our optimization bias on the Spotify data set. Here we have splitted our training data. So we have splitted our train data into the tiny and the big data set we have, right? These are tiny data set we have, right? And now in this tiny data set, we have choose the different hyperparameter on the SVM. We are using the randomizer CV. The number of grid cells that we can try. So number of combination that we can have as a 900. But when we do the randomizer CV, now we are saying that now we want to train a 900 models. Now we have a very small data set, and on a small data set we want to try a 900, we want to build a 900 model. So basically we are torturing the data, right, to get model, to kind of get the best model. And when we try to fit the model, here we can get the scores. So the score we are getting is this, right? So like over here our model is giving you kind of here we can see that it is 6.5 e raised to minus 1, so it is like 65% of the accuracy we have got, right? But one time we have got this 85% of the accuracy, 80% of the accuracy, right? But here with this C parameter, right, with this gamma parameter, right, we can see that we have got the 65, like 65% of the accuracy. But when we check on the test data, it is only 50% of the accuracy. That means here we have tortured our data a lot of time that it spell the result, right, the way we want, which, but this is not the good scenario, right? So again, there are a lot of problems we have, right? And we have to be very much careful if we have the very small data set, right? If we are dealing with a small data set, right, we can end up in like we can like we have to be very much kind of sure how to choose the best model, right? Again, why do we need a test data? Already we have said, right? So we need a test data. So the thing is, like, so that by using the test data, we can train our model, right? Or after the training, we can test our model right? So that we can be sure that our model has not looked at our test data and then it is giving you the good accuracy, right? When test score is much lower than the CV score, right? So if this happens, right, we need to try a simpler models, right? And we can even use some of the data from the cross validation data, because our test data is very small, right? We cannot do anything, right? So a machine learning works best if you have the large set of data, and there is no other chances, right? So if you have the large set of data, a lot of problem gets vanished. So the problem of biasing, problem of overfitting, problem of finding the hyperparameter, all this problem will just go away if we have the large data set, right? And yeah, this is it. This is all about the hyperparameter optimization. So as in summary, what we have discussed about the advantages of automated hyperparameter, right? So basically it is less prone to error. It is a data driven, right? We do not need a lot of human effort, right? And the disadvantages is it hard to interpret, right? And we have to be careful while passing to the validation set, right? And yeah, we also have a lot of reading if you want to know more about the parameter optimization, right? Thank you very much.